Welcome to the solutions to the Regents Physics Dynamics problem set, problems number 6 through 8. Let's jump right in with number 6 here. It is often said that 1 kilogram equals 2.2 pounds. What does this statement mean? What would be the proper way of making this comparison? Well, we have here that kilogram, of course, is a unit of mass, and pounds is a unit of weight in the English system. So to say that the two are equal to each other is really not appropriate. It's comparing apples and oranges. What this statement really means is that 1 kilogram weighs 2.2 pounds. So the proper way to make this comparison would be to say that 1 kilogram weighs 2.2 pounds. Okay? And then you can make that comparison appropriately there. We're really going to work hard in the course to make sure we're not confusing the difference between weight and mass, and to use the proper words when we say one and not mean the other. Okay? All right, next question here. Number 7. According to legend, a horse learned Newton's laws. When the horse was told to pull a cart, it refused, saying that if it pulled the cart forward, according to Newton's third law, there would be an equal force backwards. Thus, there would be balanced forces, and according to Newton's second law, the cart wouldn't accelerate. How would you reason with this horse? Well, the first thing I would say to the horse is that if it didn't get moving, it would be turned into a bunch of McDonald's hamburgers with special sauce and cheese, etc. But if that didn't work, obviously we're going to reason through some physics with a horse. I would sketch out the following diagram and have this discussion. So if we have, this represents the ground, and this is a rough representation of the lower leg of the horse, and we draw the force of the lower leg, and we call that force F. What we want to examine here is the components of this force applied to the ground and what these components do. Okay? Now, we would say here that the acceleration, that the horse is trying to accelerate that way. So the horse is walking that direction and accelerating that direction, A. So this force applied along the lower leg against the ground of this, and it could be a person, it could be a horse, it could be anything. This force does two things. It has two components. One is a Y component, a vertical component down against the ground, and the other, as you can see, is a horizontal component, Fx, that pushes against the ground to the left here in that direction. The vertical component, the Fy component, is really a wasted component. Because if you think about it, the lower leg, or the horse itself, doesn't need help pushing against the ground, down. Gravity pulls the horse down against the ground fine all by itself. It doesn't need extra help to push the horse down against the ground. But what is of relevance here is the horizontal X component pushing back against the ground. And what we note here is that this horizontal Fx component is not in the same direction as the acceleration trying to be created by the motion of the horse itself. What this says to us is that this horizontal component cannot be responsible for the forward acceleration. Newton's second law clearly says that if there's an acceleration, there has to be a net force in that direction, and the net force and the acceleration are proportional to each other and in the same direction. So then what is it that causes that forward acceleration? That force is caused by a force called static friction. We haven't talked at all about friction yet, and you're going to have a special lesson on friction coming up this weekend. But this is what causes the horse to go forward. It's the only force acting in that direction that can be responsible for the acceleration. If you really want to think about this, remove friction from the ground and have yourself, or in this case a horse, walk on a frictionless surface. Where would it go? The answer is that it would go nowhere, because there's no force pushing back on the bottom of the foot or the hoof of the horse in this case to cause the horse to go forward. So the static friction is what causes the horse to go forward. So I'd reason a horse and say, it's not your pull on the cart that causes the cart to go forward. It's static friction between your hooves and the ground that causes you to go forward. So your pull is not wasted. All right? We move on to number 8, which asks, what is your weight in newtons? All right, so here's how you do this. I'm going to use my weight as an example, and you can follow through and do the same calculation with your weight. I weigh 210 pounds. So the first thing that we have to do is convert that to mass in the metric system. And as mentioned up above in number 6, we know that 1 kilogram weighs 2.2 pounds. So to get rid of pounds, we would put pounds in the denominator of our dimensional analysis calculation here. That means kilograms goes in the numerator. And we know that 1 kilogram weighs 2.2 pounds. Pounds cancels. We divide. So take your weight, divide by 2.2. And for me, I get a mass of 95.45 kilograms. We'll take that out to 4 digits to not sig fig ourselves. Now, to figure out your weight in newtons, you simply do a W equals mg calculation. You substitute your mass in kilograms, mine's 95.45, times the acceleration due to gravity in the English system, 9.81 meters per second squared. And we get our weight by doing that calculation in newtons. Go ahead and calculate yours. Mine is 936 newtons. So that is my weight in newtons. Much, much greater, of course, number than our weight in pounds. Alrighty, that'll do it for this set of problems. You'll complete problems 9 and 10 in class tomorrow.